Hey, if you know how to find maximums and minimums, then you can apply that to real situations and find maximums and minimums that mean something in some kind of context. Like, for example, number 8. This is a sort of abstract geometric concept, or context rather. A rectangle has its two lower corners on an x-axis, and its upper corners are on the curve, the upside down parabola. I guess we'll scale that by 4s. We'll say that that's the point 0, 16. And this parabola goes like this. And that's at -4 and +4. All right. So what does this rectangle look like? I guess it looks like this, right? Where, of course, because of the evenness or y-axis symmetry of this, those are going to be at exactly the same height. And I could call this the point x comma y, or probably better, I could call it x comma 16 minus x squared, because that's what y equals. All right, so I think kind of like related rates problem, there's sort of a similar process in these types of applied max-min problems, where you need to set up some kind of drawing diagram to understand exactly what's going on, and from that get an equation. So no calculus. We haven't done any calculus yet. The thing that I'm trying to maximize, I'm trying to maximize area. So I'm just going to write that down. I'm looking for the max area. So that's telling me what calculus I need to do, what I need to look for a place where the derivative, if I'm looking for a maximum, that'd be a place where the derivative is going positive to negative. And I'm trying to maximize area. So that means I need an area function. And what is the area of this rectangle? Well, let's see. I've got this dimension of it, and this x-coordinate, this right here is x. So then the base of this rectangle would be 2x. And then the height of it would be that. That's all. And I'm going to go ahead and distribute, because I know how to do that. And it makes calculus easier. So when I take the derivative of this, now, you could just call it a prime. I think I would rather call it dA dx to just correctly acknowledge the variables involved. And I'm going to use some pretty simple derivative rules here. And I'm looking for maximum or minimum, so I'm going to set that equal to 0. Anywhere where this is 0 or undefined. Of course, this is not undefined anywhere, so I'm not going to find that kind of critical point. And then, I suppose I could do some factoring here, but that seems silly. Just solve it, right? So 6x squared, so x squared is equal to plus or minus 4 over the square root of 3. Now, what are the dimensions? Now, at this point, I think, okay, done. I did calculus. Sweet. Got the answer. But that's not actually the answer to the question that's being asked, right? So what was the question? It was, what are the dimensions of the rectangle with the largest area? So this is the x value that gives the largest area. So what are the dimensions of the actual rectangle? The dimensions would be, well, that's x, so it's 2x, right? 2 of those. And of course, we're talking about the positive. We're talking about the dimension of a rectangle. We can't report a negative number. So it's 2 of those, right? Whether you're looking back here or you're looking at your diagram, this x value is half of that dimension of the rectangle by, it's that high. So to get that high, I need to do 16 minus that. Well, x squared, I have that right there. It's 16 over 3. So that's going to be 32 over 3, if you do the math there. So those are the dimensions. You can call them length and width or whatever, but usually we report dimensions of rectangles as something by something. All right, that's how you do that. Oh, number 9, not going to do that. Number 15. Let's see. Suppose that the number of bacteria in a culture at time t is given by n is equal to 5,000 times this. Okay. Find the largest and smallest number of bacteria in the culture during the time interval from 0 to 100. That's the interval we're looking for. Now that's a closed interval, so don't forget from section like 5.3, 5.4, around that area, don't forget about maximums and minimums on closed intervals. We will have to check those endpoints. And we will be interested in finding the derivative of this. So that's just a constant times derivative of that is 0, and then here I'm going to have to use the product rule. So the derivative of the first is 1 times the second plus the first times the derivative of the second. Derivative of e to the whatever is e to the whatever times the derivative of what's up there. Okay. Now it looks like I have, if I want to set this equal to 0 to find critical points, I've got an e to the negative t over 20 on both of those. So I'm going to factor that out. With that 5,000, that leaves me a 1 here, and then minus 1/20th t. Okay, so if we're looking for zeros of this, if you want to think of these as like the factors that are multiplying together that we need to get to be equal to 0, well, that's just a number, so that's not equal to 0. It's equal to 5,000. And that, e to the something, that can't be 0, even with negative exponent. It doesn't matter. You can't get e to the something to be 0. Not possible. That's always positive. But this, I can with the number 20. What are our time units here? T. They don't say, do they? So to whatever time units they're talking about. 20. So what happens, is this a candidate for being the maximum or minimum? I guess we should just check the endpoints in this, and then that'll do it. But this is, if these are both positive, this is a line with negative slopes. So the derivative is going from positive to negative, which means this is a maximum. We should expect to see that. So we need to check the endpoints and 20. And let's see what we get. I think that, let's see what we get when we plug these in, if it's something I can do without the calculator. If I plug in 0, that just knocks that out, so that's easy. Whatever 5,000, oh, I say it's easy. 5 times 25 is 125, and then 3 zeros. I guess that's easy enough. I think the rest of them I'm going to have to do with the calculator. So 5,000 times 25 plus 100. Oh, I guess I'm doing that one first. Times e to the negative, let's see, 100 over 20 is going to be 5. So look at me. I got a TI 84 plus. I just found one. So I can do all the fancy math print. It's like you guys. I got to learn how to do it though. No. I don't like that parentheses being there. There we go. Okay, that's better. I think I have that entered properly. And that's going to be 1, 2, 3. If I round to the nearest bacterium, that would be that. And then the other thing I need to plug in, oh, did I plug that in right? Yeah, I think I did, is to plug in 20. So, see if I can bring that up and just modify this. So I'd like to do 20 there, and then 20 divided by 20 is just going to be -1 there. And sure enough, that's the biggest one, 161,788. All right, so let's see. What are the questions I'm supposed to answer here? A, find the largest and smallest number of bacteria. Here's the largest and smallest. So notice, like in our closed interval problems in section 5.4, we're reporting this number, not those numbers. At what time during the interval in part A is the number of bacteria decreasing the most rapidly? Well, when is it decreasing the most rapidly? So that means, in other words, what is the minimum of dn dt? This is a tricky little thing. This does come up, probably going to come up on the test in at least one of the questions. What's the minimum? They don't tell us explicitly what to do here. We have to piece together that this is what we need to do. So again, what are we looking for? We're looking for the number of bacteria, the time when the number is decreasing the most rapidly. So when it's decreasing the most rapidly is when the derivative is the most negative, which means that's the minimum of dn dt. That is what we're looking for. So if we're looking for the minimum of dn dt, then I need to find, if you're looking for the minimum of thing, you need to find the derivative of thing and set it equal to 0. So I need this. So let's see. Here's my derivative. So let's take the second derivative. I'll treat this like the first and this like the second, and use the product rule. So the derivative of the first is 5,000 e to the negative t over 20 times the derivative of that, which is -1/20th, times the second, plus the first, times the derivative of the second. All right, so what do we have here? Looking at factoring, I can factor this is in common between the two, and this is in common between the two. So if I'm looking for inflection points, basically, right? The 5,000 e to the negative t over 20 is -1/20, and then here I've got 1 minus 1/20t, and then plus, I factored that whole thing out, so that's +1. So it looks like that, just like we talked about before, that's never going to be equal to 0. Of course, that's not either. This is the thing that could be equal to 0. So I've got 2 minus 1 over, or t over 20, 1/20th t, however you want to write that, equals 0. So it looks like that happens at t equals 40. All right, we can check those answers in the back. I think we're good. Actually, let me just flip mine. I've got the solution manual here, just to make sure. So if we have anything to fix, we can fix it now. Check 9 real quick, or 8 rather. Yeah, 8's good. And 15, we're good. All right. Moving on. What do we got next? 19. Number 19, an open box is to be made from a 3-foot by 8-foot rectangular piece of sheet metal. By cutting out squares of equal size from the 4 corners and bending up the sides. So let's say we cut out squares where the side length is x. And then we're going to bend up the sides. Okay, and we want to find the maximum volume the box can have. So I want to find the max volume. So that means I need an equation for volume, a function for volume, and then I need to find the maximum of that. Okay, so the volume of this box, once those things are folded up, it's going to look like this. And so let's see, what are the dimensions of the box? Well, it's going to be x high, right? And then this here, that's what that would be. So that's going to be 3, but minus the 2 x's, because that's getting folded up. So this is like 3 minus 2x. And then this right here, similarly, is going to be 8 minus 2x. So the volume of a box is length times width times height. So the derivative, actually, let's do some distributing first. So let's see, if I FOIL this out, I get 24, and there's an extra x, and then I get minus 6 minus 16, the extra x, and let's double check, yeah, that's right, and then plus 4x squared, but it's going to be 4x cubed because there's another x there. Okay, now we can take the derivative. It's 24 minus 44x plus 12x squared. Set that equal to 0. And maybe I'll do a little factoring here. Looks like I can take a 4 out. And that's going to be 3x squared minus 11x plus 6. And let's see, can that be factored? I don't know. Let's give it a shot. It's not really too super hard to factor this one, or at least to attempt, because that's prime, so it's got to be 3x and x, and they'd have to both be negative, and there's not that many combinations here. They can't, let's see, 6 and 1, no, 3, and 2, 3, oh, bing, 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 bing. Okay, so it does factor. So that means x is either going to be 2/3 or 3. And I don't think that x can be 3. I think that is some serious garbage there, because this whole side is 3. So if you made this equal to 3, you'd be like cutting, that's clearly doesn't make any sense. So this must be the maximum. We could check real quick. We could just make a quick sign chart and see if this is our v prime, then what's happening with the signs. If this is 2/3 and this is 3, if you plugged 0 in here, you'd get negative and negative. That would be positive down here. And then it's going to switch signs. There's no squared factors here, so it's going to do that. So 3 was a minimum. Doesn't make any physical sense anyway. And that is, sure enough, a maximum. Now, what's the question we need to answer? for 19. Find the maximum volume the box can have. So I'm not looking for this. They're not asking me what should the side of the little squares be. They're asking what's the maximum volume. So that's plugging 2/3 into this. So that volume would be, just to kind of preserve what we're doing here, like the dimensions, I'm going to plug it in this form. So we would have 2/3 high by, let's see, 3 minus 4/3 is 5/3 by 8 minus 4/3 is 20/3. Hope I did all that right. So 2 times 5 is 10 times is 200 over 27. Do we have units here? Feet, cubic feet. Let's see how the book reported that. Yep, they did the same thing. They left it as a fraction like that. All right, great. This is fun. Number 21. A closed rectangular container with a square base is to have a volume of 2,000 cubic centimeters. It costs twice as much per square centimeter for the top and bottom as it does for the sides. And we want to find the dimensions of the container, the least cost. It's got a square base. So that's a square. Let's call that x. And then it's got some other height. And I guess I'll call that y, or 8, I don't know what you want to call it. This xy kind of makes sense. You could call it other letters, if you wanted to call that an h, whatever letters you choose. But what I know for sure is, since it's a square base, I do know that there's a relationship here between x and y. Since the volume is fixed, that x times y, that's how you would find the volume, and the volume is fixed at 2,000. So that's true, which means that y is equal to 2,000 over x squared if we needed to make a substitution. And I know that it costs twice as much. Sorry, I lost my place here. What number is 21? It costs twice as much per square centimeter for the top and bottom. So the cost is the thing I'm trying to minimize. So the cost as a function of x is equal to 2 times, it's going to cost twice as much for the top and bottom. So the area of each of those is x squared plus, and oh, sorry, it's going to cost twice as much, and there's 2 of those. All right, so I need to, this is the 2, the top and the bottom, 2x squared, the area of those, and this is the twice as much factor. And then it's just going to cost, like, you could think of this as like $2 and $1. Whatever multiples they are, it doesn't matter. You can make this 2,000 and 1,000. It would not change. It's just the ratio that is important. And here I've got $1. There's 4 of these sides, and each one of them is x times y, the area. 4 of those x times y, but this is supposed to be a function of x, so I'm going to use this instead of y. All right, let's just simplify that before we go a derivative taking. 4 times 2,000 is 8,000, and that's one of the x cancels out. I guess I'll write that as x to the negative 1, like that. Okay, so what's dc dx? It's going to be 8x minus 8,000 x to the negative 2. All right, let's set that equal to 0, which is the same as setting these two things equal to each other. You can write out that extra step if you want. So 8x is equal to 8,000 over x squared. So doing a small amount of algebra gets me to there. And what were we being asked to find? Find the dimensions of the container of least cost. Okay, so it looks like it's going to be 10 by 10 by y is equal to 2,000 over x squared. So x squared is 100, 2,000 divided by that, it's going to be 20. Oh, my drawing looks actually not terrible. So what are the dimensions? 10 centimeters by 10 centimeters by 20 centimeters. That's my dimensions. All right. Next, 47. Two particles, A and B, are in motion in the xy plane. Their coordinates at time t are given by the particle A has coordinates t comma 2t, and particle B has coordinates 1 minus t comma t. And they want to find the minimum distance between A and B. So I want to find the minimum distance, the minimum of the distance. Well, that's the thing that I need a function for then, right? So distance is equal to, just do the distance formula, right? Let's see. That's the square root is basically the Pythagorean theorem, right? So this minus this is going to be 2t minus 1 squared plus, let's make sure I get these in the same, actually it doesn't matter what order you get them in because they're both getting squared. 2t minus t is just going to be t. If you had negative t in there, that's going to get squared off anyway. So that's my distance formula. And then how about we just do a quick round of simplifying here. That's 4t squared plus t squared is 5t squared minus 4t plus 1. And I guess for calculus purposes, think of that as all being to the 1/2. So dd dt is 1/2 times 5t squared minus 4t plus 1 to the negative 1/2 times the derivative of what's inside, which is 10t minus 4. And if you would like to know where the critical points are, that's where this is undefined or 0. So 1/2, that's like a 2 on the bottom. This is the square root of that on the bottom, and then 10t minus 4. Well, if you're looking where this is equal to 0, that's going to happen when the top's equal to 0. So 10t minus 4 equals 0. That would be 2/5. And we would just need to check that this is always going to be positive. So at 2/5, that is going to go from negative to positive. And if the derivative is going from negative to positive, that means this is a minimum distance. And I think that's what we're looking for, isn't it? 47. Find the minimum distance. So this is the time where that minimum distance happens. But if you actually want to find the minimum distance, you have to do this. So where do we want to plug that in? I guess I could plug it in here into this version of it. So distance is equal to the square root of, I'm trying to do this without a calculator as much as possible, 5t, so t squared is going to be 4 over 25, so that's 4/5 after I multiply by 5, and then minus 4 times that, that's minus 8/5 plus 1. So that's negative. So that looks like it's the square root of 1/5 is the minimum distance. you ever try to just say too many words too fast? I do that all the time. Yep, that's the correct answer. And I believe we have one more to do. And I believe I'm going to need another piece of paper. There's one. 57. Where on the curve y equals 1 plus x squared to the negative 1 does the tangent line have the greatest slope? Okay, so we want to find the maximum. What are we trying to maximize here? Think about that for a second. We're trying to find the maximum of the slope. So that means if I'm trying to find the maximum of this, I need to take the derivative of this and set it equal to 0. So we need two derivatives here, right? Because I'm trying to find the maximum of the slope. I can't just find the slope and set it equal to 0, because that's where the slope's equal to 0. I need to find the derivative of that and set that equal to 0. So let's see. The first derivative is negative 1 plus x squared to the negative 2 times 2x. And I don't really know if there's any simplifying that needs to be done there. I think I'm going to think of this negative sign as belonging to this when I do the... No, I won't. Just kidding. I'll use this. This will be my first and this will be my second. So product rule. The derivative of the first is 2 times 1 plus x squared, the negative 3 times 2x, because chain rule again. That's the derivative of the first, times the second. This 2x came out because of the chain rule. That one was already there. That's the second. Plus the first times the derivative of the second. All right, so I want to set that equal to 0 to find the maximums of it. So let's see what we can factor out here. And look at this. This has kind of less stuff in it. So I can factor out... Oh, I want to show you a trick here. This is going to come in very handy. I guess it's mostly problems of this type, like Chapter 5, finding maximum and minimum type problems. When you have some kind of factor that shows up, and you're at this point kind of doing algebra, trying to factor things out, you should factor out in the same way, let me compare it to this. If you were doing like 5x to the 7th plus 3x to the 4th, and you were trying to factor this, you're going to pick the exponent that's the smallest, right? You're going to take x to the 4th out. So we're going to do the same thing here, but which one of these numbers is smaller? Actually, this is smaller. So I'm going to factor that out. And then I'm going to also factor a 2 out. Okay, now here, that's easy. I just factored the whole thing out and a 2. So what's left there? It looks like 4x squared. What is left here when I factor negative 3 of those out? Well, it'd have to still be positive 1 of them here, so that when I distributed back, I'd get back to negative 2. And the effect of that is that we get rid of all the nasty, all the negative exponent stuff that's a little trickier to deal with, is gone from in here. And this is not going to be equal to 0 because it's an upside down thing, so that's great. So now I'll be able to more easily see what x values will make this equal to 0. So I think that's all that's left here because I took the 2 out, right? So that can't be 0. This can't be 0 because it's 1 over something. And this can be 0. So got 4x squared minus x squared minus 1. So it looks like x equals plus or minus the square root of 1/3. And what's the question? Where on the curve? Well, that's an x value. So right there on the curve. We did it. Oh, but what about maximum, minimum? Do we know? We want the maximum. So I don't know. There's two here, and I don't know if they're maximums or minimums here. So I guess I need to do a little sign chart of this second derivative. So I've got negative square root of 1/3 and positive square root of 1/3. So let's see what's happening with the signs of this. I've got a nice factored version of it here. So this is going to be positive. Of course, it's just the number 2. Let's plug in something like -1. If I plug -1 in, I get 1 plus 1 is 2. Oh, this is something plus something, so this is always going to be positive. I don't even need to worry about that, right? Because that's always positive, and this just flips it over. So that's always positive. So the only thing I'm really checking is the sign of this. So if I plug in -1, that's positive. If I plug in 0, it's negative. And then if I plug in 1, it's positive again. So I'm looking for a maximum. That is going to happen positive when the derivative goes from positive to negative. So this is the max, and this is the minimum. So max slope at x equals negative square root of 1/3. I went over 30 minutes. You get a free pizza.